Section 2.3 is all about analyzing graphs. So we have three things to talk about in this section. We need to talk about some requirements of the title, the axes, and the source of any graph or chart that you create. We need to talk about graph appropriateness, which is kind of a big deal. And then finally, we're going to talk about scaling graphs and the shape of graphs. So, when you're making a graph or a chart, every graph requires a main title, and there may be multiple other titles. So, for instance, you could have in a bar graph your bar titles. They all need to be titled somewhere. On a pie chart, you need your pie wedges to be titled, so people know what they are. On your histograms, you need your class titles. And there's a bunch of others, but you need a main title at the top of every one of your graphs or charts. For your axes, these need to be labeled. And this is when appropriate. Sometimes you don't need to label an axis if appropriate. You don't need to label an axis if it is obvious what it is. So for instance, if your bar graph, all of your bars are labeled underneath, the x-axis does not need to be labeled because it's not representing anything. It's just a function of what the graph is doing, separating your classes. Graphs always need to be sourced. So they need to source their data. Always, big old letters here. So you would never show someone a graph and say, oh, it represents this data without sourcing the data so they could confirm that on their side. It's a really important thing to make sure that you're not falsifying any graphs. And then finally, appropriateness. We need to choose the type of graph. So we always choose the type of graph that matches the data. So for instance, you wouldn't want to use a line graph, which is exclusively or almost exclusively used for time iterations, for something like our TV example that we've been using this chapter. You want to make sure you're picking your graph that matches the data properly and displays the data in the best way for what you're trying to get across. So we want to talk about two different types of graphs that you can see: time series graphs versus cross-sectional graphs. So knowing the distinction between these will allow you to pick the proper graph. So a time series graph these are line graphs primarily. That display one variable over time. So for instance, if you're measuring how tall you are when you're growing up as a kid every 6 months, that's a time series graph. You're only measuring height. But if you were measuring the height of all of the neighborhood children, you wouldn't want to do that as a time graph because you're just taking one snapshot of data, and that's what cross-sectional graphs are. So cross-sectional graphs display data collected only at one time. Now there is one other type of graph that gets sometimes used, and those are pictographs. And so these are essentially bar graphs. That use pictures. Instead of bars. And you can see an example on page 99 of our textbook. Pictographs we're basically never going to use. They're not useful in statistics as much. They're more for when you're trying to display something specific and you're trying to link it to whatever you're doing. So maybe you're doing a bar graph about a deli store and you use sandwiches as the bars instead of bars. But again, pictographs we're not going to use in this class, but they are there, and you can look at page 99 to see an example of that. So the next thing about graphs that we're going to talk about is scale. So scaling your axes on any graph is very important. If there is nothing you remember from this section, remember that scaling is extremely important. And the reason for that is because bad scaling can distort your data. It can distort the data and misrepresent what is actually happening. And this is actually something that occasionally happens on purpose. If I want to purposefully deceive someone, I can misscale my axes and make it look like something it's not. So I'm going to give you a quick example here of raises to illustrate that issue. So let's say you're applying for a job and you get the job, or you're in the interview and they say, do you have any questions? You say, well, I'd like to know about how you administer raises. And they say, well, we have this great chart that shows our progression for salary or for hourly workers. And they say it's dollars in raises compared to years of service. And you go, okay, that makes sense. No problem there. And they have some tick marks here. And we have 1, 7, 10, 25 years of service. And down here we have 1, 2, 3, 4, 5, 6, 7. And these are labeled as 1, 2, 5, 12, 21, 30, and 80. And so your chart looks like this. Let's change the color to make this stand out a little bit here. So we have, drop my pens. So we have one point at 1, 1. Then we have another point about right here. And then we have another point at 5, and that is here. And then we have another point right here, which is right there. And then we have another point way out here that's here. And they have this nice graph that does this. And you look at this and you go, okay, that's not terrible. It looks like I get some raises a couple of years. I get a good dollar amount, even get up to $80 raise. And then you have to remember that this is so ridiculously scaled. You get a dollar raise after 1 year, and you don't get another, let's say, $3, which is only a $2 increase from your first raise, for another 6 years. And then, yeah, you get another raise up to 5, which is, again, only $2 after 10 years. And then after what looks to be about, I don't know, let's say 10 years, you get or after what? Between 10 and 25, you get a $10 raise. You're up to $10 right before 25 years of service. And your $80 raise doesn't come until you're at whatever this is that they haven't labeled. So it looks like these happen in rapid succession, but in reality, after 25 years, you've only got like 10 bucks total from when you started. And it looks horrible. So if you scale this properly, 10, 20, 30, 40, 50, 60, I need a longer axis, 70, and 80 way out here. So if we have axes scaled properly, and then on this, we would have something like 5, 10, 15, 20, 25. And now our data points, this 1, 1 is really right here. Then the 2, that gets you the 5, or the, yeah, that happens at about 5 years is really here. And then the next one that's dollars is about 10, and that happens at about your 7-year mark, about right there. Oh no, that's your 5, that's right here. The $10 raise is your, what is that? $10 raise is the 25. The $5 raise is at 10. So that's about here. So let's drop this there and there. Get rid of that point. And then the next data point isn't until way out up here. And then your next data point isn't until way out here. And now you see, again, this is your dollars, and this is your years of service. You actually see what happens more frequently. You get a couple raises spread relatively close together at the start of your career, and then you have to wait a long time to get that next raise, and then you have to wait even longer to get the big one. So you have a long period of time where you're not making more than $10 more than what you started with, which is not great. So scaling your axes is incredibly important because you can distort what's actually happening to make it look better than it is, or you make it look worse by mistakenly scaling your axes poorly. So what we want to talk about now is our histograms. As we said in the last section, this is going to be our primary graph that we look at. So we need to be able to understand the most common shapes that we'll see. So the first shape is uniform distribution. And this means the frequency of each class is about the same. About the same. We have symmetric distribution. This means that the data has a D. Data lie evenly on either side of a vertical line. This is the classic bell curve that most people have heard of. So one thing I have to mention, I always have to mention this, data lie is not improper. Data is both singular and plural in the English language. It's a weird word. So if you think that sounds funny, it does, but just know that you're going to see that. Then we have skewed left. Now this is a weird term because skewed left actually means the majority of the data falls to the right side of the x-axis. So you can make a little note here. I'm writing big, but you can see page 100 or 101 to see these definitions, the way the book describes them, and also the pictures we're going to go over in a second here. And then there's skewed right, which means the majority of data falls on the left side. Of the x-axis. So it's a little opposite of what you would expect. And there's one final distribution, and that is random distribution. And this just means there's no real pattern. So you have uniform, symmetric, skewed left, skewed right, and random. These are all distribution shapes that your histograms can take. So now we're going to look at some examples, some pictures of them on the next page. So these first two, both of these are symmetric. So this is the classic bell curve that people know about. This is still symmetric even though it is not a bell curve, because I could draw a line right here and it appears to mirror itself. Now the examples I've taken here are perfect symmetric data, but you're not necessarily always going to have perfectly symmetric data. If your bar here is this high instead, and this bar is this high instead, that's still relatively symmetric. It's just an overall shape that we're looking at. This guy here, our data is primarily on the right side, so this is skewed left. And the way that we think about this is it's skewed left because that means that more of the stuff is not over here on the left. Another way that I think about this is someone's flattened it from the left side. You've pushed it from the left, so it's skewed from the left side. And then same thing for skewed right, which is this shape here. Here we see that the data looks like it's been flattened from the right side. Most of our data points are lying on the left, so this is skewed right. And that's just something you'll have to get used to. Skewed left means data's on the right, skewed right means data's on the left. Here we have uniform distribution. Everything's basically about the same. And here, there's no real pattern here, so this is random. You have big stuff here, small stuff interspersed. There's not really a pattern here, so this is random. Okay, so that's the end of 2.3, and with it, Chapter 2 comes to a close.